Okay, so good morning again. This is the third lecture of the LLM course. Okay, and today we are going to discuss language model. So the course is about large language model. Let us first discuss what is language model. Maybe this lecture and the next lecture, half of the next lecture, we'll try to finish language model, the statistical language model part of it, and then we move to the concepts of word embedding and then neural language model. Okay, so but first thing first, breaking news as usual. Okay, so in the last class I mentioned that on 23rd, right, llama 3.1 was introduced yesterday, right. Mistral, so Mistral launched their new version, new large model. This is a 123 billion model, right? And if you know more about the model, this is the website. This was released yesterday, and this model is capable of handling 11 languages now, right? French, German, Spanish, Italian, so on and so forth, right? With 80 plus coding language, right? And the model has already been tested and compared with llama 3.1, which was introduced just 2 days back, right? And the largest llama model was basically used for comparison, and it shows comparable results on code generation, mathematics, and reasoning tasks, right? So it is comparable with respect to llama 3.1 and GPT-4o, Claude 3.5 Sonnet, and so on and so forth, right? The context size is 124K. So so every day we'll see new breaking news, and maybe I'm also not sure at the end of the day whether this course will at all be relevant or not, because you'll see new results, new models, new techniques. But the hope is that at least some of the foundations that we are going to teach, we're going to discuss, the foundations will be helpful to understand these new models. Okay, now let's move to the topic, statistical language model. Okay, so the idea of language model goes back to early 1950s. Okay, when Claude Shannon is the, right, you know Shannon's entropy, right, information theory. So goes back to 1950 when Shannon introduced this game called the character guessing game. Okay, so he was essentially playing this game with his wife, right? And basically the idea is that you give a sequence of characters and you ask the other person to guess what is going to be the next character. Okay, and it turned out that his wife actually guessed all the characters quite easily, right? And when I talk about characters, English characters, there are 26 characters plus space is another character, so 27 characters, right? So most cases it turned out that the wife essentially, so she was able to guess the next character in 3 to 4 attempts, right? The worst case she took 8 to 9 attempts, but most cases on an average she took 3 to 4 attempts to essentially guess the next character. Okay, if you look at the number very carefully, 3 or 4, right? Let's say 4, right? It has a very interesting relation with the entropy of English language, right? We all know what is Shannon's entropy, right? What is Shannon's entropy, by the way? What is entropy? Huh? Number of random guess, measure of randomness. Okay, or average information. Okay, anything else? Measure of randomness. Okay, how do you measure it, right? And if you think of this x, right, as the character, right, and px, let's assume that all these characters are equally likely. There are 27 characters, right? So this px is 1 by 27, right? So if you do this math, you see that this is essentially same as 4.3, 4.2, right? Why I mentioned this? Because you will see at the end of this chapter when I talk about perplexity, right? Perplexity is a measure is a metric to use the perplexity is used to evaluate a language model, we will see that there's a very nice relation between perplexity and entropy. Okay. Nevertheless, so this is all about guessing the next character, guessing the next word, right? And we essentially guess words almost every day in our life. Can somebody tell me where we use this guessing game? Or not we, maybe the tool, or maybe some system, some model, right? So when we type something on Google search query, right, we see this auto completion, right? The Google search engine actually shows possible words that can come after the character, after the sequence of words. So this is word prediction game, right? So let's look at this example. I like pizza with lots of dash, right? So it can be cheese, can be corn, can be tree also, right? We have I already mentioned there's a concept of vocabulary. We already have a vocabulary where there are words, possible words taken from the corpus, right? So any word from the vocabulary can essentially come here. Okay, but if the language model is good enough, the language model will say that the probability that the word cheese will come here, right, is higher than the probability of corn coming here and than the probability of tree coming here, right? So application wise, as I mentioned, there are lots of applications. One of the applications is speech recognition. Let's say if you say that I bought fresh mangoes from the market, right? Let's say somebody spoke something and you recorded it and now you translate it, right? And people like non-native English speakers, right? Their speaking is very different, and if you translate the speech to a text, it may happen that you mistakenly consider market as mar or kit, right? Or let's say if you have this sentence, I love eating spicy samosa, you can translate it to I love eating spicy samosas, says, right? Something like that. So if you have a language model, your language model will say that the probability of this sentence is higher than the probability of this sentence, right? And that information can basically be useful for speech to text translation. Okay. Similarly, machine translation deals with translating translating from one language to another language, right? Let's say if you are confused between this, let's say heavy rainfall or big rainfall, right? Big brother, large brother, right? So the model should be able to say that heavy rainfall is highly likely than big rainfall, or the festival of lights is highly likely than the festival of lamps, right? And so on and so forth. Remember, here we are not only looking at syntax but also semantics, right? Lights and lamps are quite synonymous, right? But in the context of the festival of light is highly likely than lamp, right? Similarly, family gathering is highly likely than family meetings maybe. Okay, so therefore oftentimes we say that language model is so simple, but language model oftentimes captures not only the grammar but words knowledge. Okay, it is also used in spell checking, natural language generation, and so on and so forth. There are lots of applications, right? Machine translation, as I mentioned, this is one application. Let's say you are translating English to Hindi, right? Here you can use machine translation language model. Let's say you are using let's say you are checking the spelling correction in tools like Grammarly, right? You see the language model can be used here. Of course, ChatGPT is a language model, therefore it uses not statistical language model, but the concept of language model underline the framework. Okay, so let's define language model. Language model is the probability distribution over a sequence of tokens. Very simple definition. Probability distribution over a sequence of tokens. The sequence of tokens can be sequence of characters, sequence of words, sequence of subwords, sequence of numbers. It can be anything, right? So w1, w2, dot 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 wn, there are n number of tokens, right? We measure the probability of the sequence. So this is same as, because this is a joint probability. Okay, we can essentially unfold it using chain rule, and then this is going to be p of w1 times P of W2 given W1 times P of W3 given W1 W2, right, times dot 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 P of Wn given W1 dot 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 Wn minus 1, right. So these are all conditional probabilities, and these probabilities are conditioned on the context. So the first component is conditioned on a unigram W1, this is conditioned on a bigram, and this is conditioned on n minus 1 gram. So this is an example. The monsoon season has begun, so you can essentially compute it using chain rule. This is the chain rule I already mentioned. Okay. So now the question is, how do you, let's say, how do you measure this probability? Probability of monsoon given the, or probability of season given the monsoon. What do you think? You were already given a corpus. It's a significantly larger size corpus, right? So how do you measure this probability? It's very simple. You first measure the count of the monsoon. This is going to be the denominator, and the numerator would be count of the monsoon season, right? So out of all the cases where the phrase the monsoon appears, how many cases essentially the term season follows the monsoon, right? Very simple. But the problem here is that as we increase the size of the context, right? So this is our context. As we increase the length of the context, it would be very difficult to find even a single appearance of the context in the corpus. Think of this one, right? Okay, so the numerator is the monsoon season has begun. Sorry, the denominator. So now the numerator is the monsoon season has begun. That's the numerator, and the denominator is the monsoon season has. And this is in fact small context. If the sentence is longer, then the context size would also be longer, isn't it? Right? So this count is going to be 0 or whatever, infinity, right? So if if in this probability, if one component is 0, then the entire probability is going to be 0, right? This is the problem. Okay, so to address this problem, let's see what we can do. Can we make some assumption? Okay, so the assumption that we make here is the Markov assumption. Some of you have taken automata theory, right, or some other theory where we have seen a Markov process, finite state automata, and so on and so forth, right? What is the Markov assumption? What is let's say a first order Markov assumption? Can somebody tell me? The first order Markov assumption says that so Markov process, as we all know, this is a state space model, right? There are states are connected through transitions, and these transitions, different transitions have probabilities, right? So you start from S. This is, let's say, S1, S2. A states S3, S4. A states, let's say, this is the start state. This is the end state, for example, right? And let's say you are at this state, and you are confused whether you want to move to this direction, or you want to move to this direction, or through this direction. Okay, so best option is that you look at all the states that you have traversed through so far, right, and then you make a decision, right? But storing the entire sequence of previous states that you have already encountered would be computationally expensive, because you have to store everything, right? So here you make some assumption. We say that, okay, instead of looking at all previous states, let's look at only the previous one, or the previous two, right, or the previous three, and so on and so forth, right? So the first order Markov assumption says that the transition probability is only dependent on the previous state, right? Second order, previous two states, last two states, and so on and so forth, right? Here also we say that when we measure this probability, let's say this probability, okay, we will not look at the entire context, but we will only look at previous two words or last two words, last three words, and so on and so forth, right? So this is Markov assumption, right? And depending on the number of words, number of previous words that you consider to measure the probability, we will essentially call this assumption as unigram assumption, bigram assumption, trigram assumption, right? Fourgram assumption, and so on and so forth. If it is an unigram assumption, it means all the words are independent. So the monsoon rain has begun, probability of the sequence is equal to probability of the times probability of monsoon times probability of has times probability of begun. This is called unigram assumption. Unigram assumption is equivalent to the zeroth order Markov process, right? Where it is not dependent on the state at all. Okay, so we take this, we make these assumptions, n-gram assumptions. N-gram is equivalent to n-gram is equivalent to n-1 Markov assumption, right? Order Markov assumption. Okay, so if we take unigram assumption, then this is essentially same as the multiplication of all the unigram probabilities. If it's a bigram assumption, then we will only look at the previous word, right? If it's a trigram assumption, then we look at last two words, and so on and so forth. Okay, so then this is equivalent to in case of, so if you measure this conditional probabilities, in case of unigram, this is equivalent to P of begun, right? In case of bigram, this is equivalent to P of begun given has. Yes, if it is trigram, this is begun given season has, right? And so on and so forth. So we are now restricting our context size, context length, right? If we restrict the context length, what would happen? It is highly likely that you will encounter the context in the given corpus, right? So it is less likely that you will see a zero occurrence. Okay, now here is a question. Think about it very carefully. So unigram assumption says that all the words are independent of each other, right? But in English, I mean in all the other languages also, words are not independent at all, right? Now as you move from unigram to bigram to trigram to fourgram to fivegram, what actually happens is that you capture more context. More context means more grammar, better grammar, right? So it is obvious that as we move on, right, we would be able to capture better grammar, and the English that you generate, if you use language model to generate something, you basically generate better English. But at the same time, the probability is also going to be zero, less like highly likely, right? So it's a trade-off. If you move to this direction, to the lower order of Markov chain, Markov assumption, then the probability is not going to be zero, but the English will be essentially meaningless. If you move to this direction, English will be better, but the probability is going to be zero. I mean, likelihood wise. So we try to restrict ourselves to somewhere between 3 to 4. So generally 3 gram or 4 gram is the right choice for language model. Okay. Okay. So let's now focus on bigram, because bigram is something which you can easily understand, right? So let's assume that our language model that we are focusing on is a bigram language model. Okay. So how do we measure this probability? We need the bigram count in the numerator, right? Count of xi minus 1 comma xi by count of xi minus 1, right? So bigram count by unigram count. Clear? Bigram count by unigram count, probability of monsoon given the, right? Probability of the monsoon by probability of the, right? So bigram count and count, bigram count and unigram count, right? So to do this, we need a table of bigram counts and unigram count. Okay, so this is a bigram count table, and this table is essentially constructed from the document. We are given a huge corpus. Assume that you are given a huge corpus. You basically traverse through the document, you create the vocabulary, right? And this is a bigram count table where rows are vocabulary entries, columns are also vocabulary entries. This is a square matrix. Clear? Now each of these entries indicates the bigram count. So 827 indicates the number of times the phrase "I want" appears in the document. This is asymmetric. Okay, this is not want I, this is I want count. Okay, now this indicates how many times the phrase "to eat" appears in the document. Obviously you ask why this is 5, I, right? Why this is 5? What do you think? Let's say sometimes when we let's assume that this document is essentially a translation from speech to text, right? And if somebody fumbles, so I, right? So this is just an error, but there can be many such errors. Okay. Okay. So this is the bigram count, and this is the unigram count. Unigram count is very simple. We look at all vocabulary entries and we see how many times. Can somebody tell me from the bigram count, can we guess the unigram count?
Yes.
How? Summation of? Okay, the next question is, what do you think from this, in this table, if you look at a single row, right? Sum of the entries of this row, is it equal to the sum of entries of the column? Let's assume that this is exhaustive. Let's not focus on the numbers here. It's just a sample number table, right? Let's assume that you have this the actual bigram table, right, where rows are entries, columns are entries, and and every entry indicates the count. What do you think? So what do you think? The sum of these entries, would it be same as the sum of these entries?
No.
Are you sure?
Yes.
How many of you think that this is not the same? How many of you think that this is the same? Don't hesitate. So the answer is yes. Okay. So the answer is yes. Sum of row entries for a particular row would be same as the sum of column entries for the particular entry, right? Now think about it. Why? Okay, so let me explain why. Okay, so although this is not a symmetric matrix, right? But think about it. The word I, right, appears with so let's say you are interested in W1, W2. This is the template of the bigram. Okay, and these row entries indicate those cases where I appears as the first word, which is W1, right? All possible cases where W1 is basically I, right? Now look at this one here. This is all possible cases where I is essentially the second word in the bigram, right? If I is the second word in the bigram, so the first word can be anything in the document, in the vocabulary list. Yes. Now, right? Now tell me a case. Can you think of a case, right? Or can you think of a bigram which is not considered in rows but considered in columns, or vice versa? Yes. Very good. So first and last word, right? But remember, start of a sentence is also a token, and end of a sentence is also a token in the vocabulary, right? So there'll be a row which corresponds to start of a sentence. There'll be a row which corresponds to the end of a sentence. That case, right? So the sum would be same. Wonderful. Okay. Okay, let's move on. So from the bigram table and the unigram table, now we can just take the ratio of this and this, right? And we get the bigram probability table. So this is the bigram probability table, where the numerator is the bigram count and the denominator is the unigram count. Okay. Look at this table very carefully. This is a subset of the table. Now think of a million size vocabulary, million cross million matrix, right? Most of the entries are 0. Most of the entries are going to be 0. In fact, in this specific corpus, this Berkeley restaurant project, 99.95% entries are 0. Okay, this is the number that this is not a number that I am making it, right? This is a number that was already proven. 99.95% entries are 0 in this bigram matrix. Okay, this is so sparse. Now, what is the, let's try to understand the meaning of this 0 entries. The 0 entries are those which never appeared together in the document, right? It doesn't mean that those 0 entries are invalid entries. Okay, let me give an example. Let's say in your document the word enjoyed, right, appeared with the set of words like the movie, enjoyed the food, enjoyed the game, enjoyed the vacation, right? So if you draw this this matrix, you see that let's say trigram matrix, you see that enjoyed and these trigrams, their entries are non-zero. But in the test set, suddenly you see enjoyed the festival in your test set, which was not there in the document, in your training document. So if you look at the bigram table, the corresponding entries enjoyed the festival, corresponding entries will be 0, right? But this should not have been 0, because this is a valid phrase, right? But it is not the case that all the zeros actually qualify for this. Meaning, it is not the case that all the zeros can be grammatically correct or semantically correct phrase, right? Of course, most of the zeros are meaningless, right? For example, if you look at here, right, eat, want can never appear side by side. Right? Two verbs can never appear side by side. Food, want again never appears. So this bigram table actually tells a lot of things. Although it looks like a statistical table, right? But it also indicates many important aspects. For example, let's say you see that let's say Chinese food, right? Chinese food, you see the probability is quite high, 0.52, right? Let's say 1, 2 is 0.66. So 1, 2, if you see the entry, the probability is 0.66 for 1, 2. You can say that this is so 1, 2 is essentially grammatically it is basically something. It is talking about grammar, right? Whereas Chinese food appears a lot of times in document. It basically indicates some sort of world knowledge, right? What about let's say two food? Two food is 0. Can you imagine a sentence where two food appears? Huh? I can't express my love to food. Okay. What else?
I went to food stall.
Okay, to food. I went to food stall. Right. So the number is 0, and this 0 is called contingent 0. Why this is contingent 0? The contingent 0 means it will be hard for you to think of a sentence where two food appears. If I ask you to think of a sentence where Chinese food appears, right? you can easily think of a sentence where Chinese food appears. But if I ask you to think of a sentence where where two food, the bigram two food appears, you will pause and think of a sentence, then you articulate. Okay, so this is called contingent zero. Okay, so the other problem of n-gram language model is that this long range dependency. Okay, so if you look at this sentence here, the project which he had been working on for months was finally approved by the committee. Okay, now here approved is referring to the noun project, right? But if you take a 2-gram language model, bigram language model, trigram language model, so and if you ask the trigram language model to predict, let's say this is the context till this part, and you ask the language model, a trigram language model or a 4-gram language model, that what is going to be the next word, it will fail miserably, because last 4 words can't determine the word approved. Okay, look at the last 4 words, on or for months, comma, or months, comma, was finally, right? Now the language model will be able to say the next word is going to be approved, right? So if you had a language model whose context size is 10, for example, right, or 12, for example, then the language model may be able to guess the next word as approved. But you know the other problem, right? Count 0. So we'll see when we'll talk about RNN, specifically LSTM or GRU kind of models, we see these kind of long range dependencies are addressed, right, by this kind of gated recurrent neural network. Any query? Okay, so we already have seen how to estimate these probabilities, conditional probabilities. We use maximum likelihood estimate, MLE, and MLE says that if you want to predict this conditional probability, you essentially this is the best possible probability estimate that you can think of, right, given a particular document. Okay, so I already mentioned about the limitations of this MLE estimate in graph language model, is that if you have an unknown phrase which never appeared in the training set, right, but it's a valid phrase, you will see in the test set it is going to produce a 0 probability, right? In fact, there are cases where the words or the tokens in the test sentence, right, they are not a part of the vocabulary at all. Remember, the vocabulary is constructed from the training set. You have a training set, right? You scanned the training set, you created the vocabulary, right? Now, a test set is independent of the training set. It may happen that a test set, right, one phrase or one word is completely unknown. Let's say LOL, right? I mentioned last day, all these social media languages, right? Then what you do? If it appears in the training set, right, and if the entries are 0 in the training set, you can do some tricks and then you can adjust. But if it never appears in the training set, then in the matrix that you constructed, there is no entry, right? And what do you do? What do you think? What do you think? So this kind of case is called OOV, out of vocabulary token, right? So out of vocabulary tokens are those tokens which are present in the test set but not in the training set. Therefore, this is not present in the bigram table or trigram table, right? So how do you deal with this kind of words? What do you think? So I'm asking those who have not, who have never taken NLP course. What do you think? How do you deal with this unknown words? And then You create a separate dictionary for the unknown words with the unknown words, or what? And then what?
Put it on search.
Where do you search? It never appears in the training set. Yes.
Like what word can come at the place of we have a sentence and it's LLMs. We don't say instead of LLM in the literature it would be like funny or something.
Okay.
And then from funny we can predict.
Oh, okay. That's a very good suggestion. Okay. So what he's saying is that, let's say the unknown word is LOL, right, which essentially is used as a replacement of whatever, laugh at loud or whatever, right? So it's a funny kind of phrase, right? So you look at the context where the similar words appear in the training set, and maybe you use that as a proxy for the probability of LOL. It's a good idea, but what we generally do is that, now remember, for all these things, to basically check the similarity and other stuff, right, you need tools. You need external thesaurus like WordNet, right, or some other means by which you can say that this is similar to this, right? So statistically, when you talk about statistical inference, so statistical inference is independent of any tool.
I'm saying that do not use similarity. Just predict what word can come to. Like if it is LOL, don't use the LOL.
So what you are saying is that you look at the context,
and
right?
Predict what can come at the place of.
So you look at the context and you see what are the other words which appeared after the context in the training set,
yeah,
right? And you use it as a proxy of that.
Like basically the task is to predict word which is next to L1. So instead of this task, we create a new task to first predict what could be at the place of L1, and then using that another task.
Okay, that's a good suggestion. But what we do in general is that we so while creating this vocabulary, right, we also maintain another list which we call as lexicon. What is a lexicon? A lexicon is a subset of vocabulary, right? And in a lexicon we generally store those tokens which have a certain which have a frequency above certain threshold, right? Let's say you sort all the tokens based on the frequency, right? And let's say the cutoff of the frequency is 5 or 6. So you consider all the other tokens whose frequency is below 5, right, as a proxy of unknown. Clear? So from your training set, now you have a lexicon, and the vocabulary minus lexicon, that subset acts as an unknown token, right? So in your bigram table now, you instead of entries which are there in the vocabulary, now we have entries which are there in the lexicon, plus an entry which is unknown, UNK, UNK, right? We use the token UNK, right? And what is this UNK? This UNK essentially constitutes, all this UNK corresponds to all the entries of the vocabulary whose frequency is below the threshold, right? Now whenever you encounter a new token in a test set, right, you first fetch the probability corresponding to UNK from the training set, and you use this to measure the probability. Any question? Yeah.
Right, we aren't losing the information.
Yeah, we are losing the information. Yes. Yes, we are losing the information, but I mean, that's the simplest option that we can think of.
So can't we also preserve the words which are?
So then the probability game will change. Remember, the probability needs to be 1 and so on and so forth, right? So that also needs to be satisfied. It's a probability. Okay, let's move on. So let's say you first scan the entire document, right, and you basically noted the frequency of all the tokens in the document, right? You sort all the tokens based on the frequency. You fix a threshold. Let's say threshold is 5, right? You consider all those tokens whose frequency is below 5 as UNK, right? Now you have a single token called UNK, right? And the other lexicon entries are also there in the bigram table, and then you do the similar kind of measurement that we did earlier. Yes.
Is it possible to get one word possible to get also to get yes, also to get
That's a very good question. So it also depends on the application, right? So in general, what we do, in general, we consider cat and cats as two different variations, and we keep those entries separately in the bigram. So these are tokens; these are not types, right? So the difference, these are two different vocabulary words. Yes.
but if that is possible, then what to decide on this also what to have. So that
But then you also need to consider the combination, right?
yeah, so I
CA.
so what do I do that one which is that is
Yeah, that can also be possible. So what Chetan is saying is that uh, along with the vocabulary words, right, you also consider the characters and the combination of characters as tokens, right, and you put everything to the bigram table, right, and let the count be 0, right, and when we do the normalization, we take care of the way we essentially take care of the 0 entries. That can also be possible, of course, but the problem is that maybe a possible problem would be the number of combinations that you have would be significantly large, and then the size would be
this is the problem that if I get CAT, then I can CAT and CAT.
Mhm.
But I don't like it. The same problem which happened to the cat.
yeah, exactly. So I mean, again, as I mentioned, it depends on the application. Most cases we consider cat and cats as two different entries in the matrix, but some cases we first do some sort of stemming and then consider. Okay, let's move on. Let's now discuss some of the smoothing techniques. Okay, so why do we need smoothing? Because we have already seen the matrix is quite sparse, right? 99% entries are 0, and we need to smoothen it somehow. The simple way of smoothing is that you blindly add +1 to all the entries in the bigram table, right? This is the bigram table. You add 1 to all the entries in the table, right? If you do that, what would happen? So now, so this is called add 1 estimate. It's a new smoothing technique. We add 1 to the numerator. If we add 1 to the numerator, right? Let's say you add 1 here. You add 1 to all the bigrams. Remember, bigram count is a numerator in your probability, right? You need to make sure that the conditional probability, meaning P of, in this case, let's look at the first row, P of I given X can be anything here, right? Sum of this should be 1, right? And so this is essentially count of Xi by count of X. So you added 1 to the numerator so far, right? If you add 1 to the numerator, then the probability would exit, basically cross 1. So we need some sort of adjustment here, right? What would be the adjustment? So think about it, right? So when you add +1 to all the entries here, how many ones you are adding? For every entry, let's say for entry I, how many ones you are adding? Number of columns, and number of columns is same as number of vocabulary, right? So if the vocabulary size is indicated by V, then you are adding V once, right? So if you normalize it, right, by V, meaning if you just add V to the denominator, then this is going to be 1. Clear? Okay, so this is called add 1 smoothing. right? 1 is just a number. You can add 0.5, you can add 0.2, you can add 3, 4, 5, right? So in general it is called add k smoothing, right? So you add k to the numerator and kv to the denominator. Clear? Okay, so after this, once you did this, so the resultant count would change. Think about it. This is your probability, and you just made an adjustment to the probability. Okay, so this is your probability. So because of this, the bigram count will change, right? Now let's look at the resultant bigram count. So this is essentially same as your new bigram count, which is C star, and the old unigram count, because I did not change the unigram. Remember this. I only changed the bigram table, right? I only changed the bigram table. Unigram table remains the same. So C star is my resultant bigram count, right? So if you do the math, so C star is essentially going to be this times the unigram. So this will come here, unigram count. Okay. So this is your new bigram count table. Just look at this table and try to remember the table briefly. Okay. And also, and what is this? This is the table after adding 1. Okay. And this was the initial table. So this was the initial bigram count table. You see a lot of zeros, right? And this is my new bigram count table. Okay. Let's compare these two tables side by side. So earlier all the zeros, there were lots of zeros. Now you see there is no zero here, right? But there are some issues. What is the issue? The issue is that let's look at some of the high frequency words, right? 827, it is now 527, right? 608, it is now 238, right? 686, this is 430. A massive drop, right? So you know this add one smoothing, essentially, I mean, in a funny way, we say that it essentially steals the property from rich and distributes it among poor. Okay. So, but the problem is that we have so many poor people in our society that even if you steal something from rich, you'll have to steal a lot, right? So the high count will be reduced significantly, whereas the low count, look at this one, 5 will remain almost the same, 3.8, right? So middle income people, they are not affected. Okay. So but this is problem. This is a problem. Why this is a problem? Because now the actual count is not reflected properly in the resultant matrix, right? This is the problem of advanced smoothing. So to address this, we will discuss more advanced smoothing techniques. Okay. So this is the add k smoothing that we discussed so far. We added k to the numerator and k into v to the denominator, right? So if you think of k into v, right, as m, right? So then k is essentially m by v, right? So we replace k by m times 1 by v. By the way, I'm misusing the notation actually. So in my notation, v is the size of the vocabulary, and in this slide in the notation in the slide, v is the set. Okay, mod v is the size. Okay. So what I'm doing now, I'm replacing k v by m. So now k is going to be m by v. So now I replace k by m into 1 by v and kv by m, right? Now if you look at it carefully, this 1 by v is what? 1 by v is essentially the case where this is it's uniform, right? All the vocabulary words are equally likely, right? But so essentially what we are doing, we are essentially adding uniform, basically uniform, some sort of uniform probability to the numerator with some constant m, right? So instead of this, what you can do, you can replace this by a probability, a unigram probability. Instead of making it uniform, now you essentially replace it by unigram probability, because this uniform 1 by v is same for all the vocabulary words, isn't it? It is same for all the vocabulary words, but that should not have happened, right? So now what I'm saying is that let us replace this by PWI. What is PWI? PWI is something that you are predicting. Now this probability is dependent on the current word that you are considering. Okay. So and then how do you measure this H and M and K? We can measure M and K using the held out data set, the validation data set, and you can essentially do hyperparameter tuning. Yes. P of WI is the uniform probability from the corpus, right? Okay, so a bit more advanced method, although they are also very simple, can be backoff and interpolation, right? In backoff smoothing, what we do, let's say we are interested in trigram probability, right? And we saw the trigram probability is 0. So we basically back off and we move to bigram probability, right? And we see the bigram is also 0. Then we move to unigram probability, and so on and so forth. Again, some sort of approximation. Remember, this approximation may not result in a true probability value. Remember this. This may result in some number which may not satisfy the probability rule, right? But still, in a larger context, it is still useful. Interpolation is another approach. Interpolation says that, let's say you are interested in trigram model, right? Probability of Wn given Wn minus 1, Wn minus 2, a trigram model, right? So this is, in interpolation, this is essentially a combination, a linear combination of trigram probability, bigram probability, and unigram probability, right? With certain constraints, lambda 1, lambda 2, lambda 3, such that sum of lambdas should be 1. Again, you see this is p hat. This is not a probability. Clear? Okay. Now you can again think of more advanced version where you say that instead of this raw probability count, right, I make this probability dependent on the context. Okay. So now this lambda 1, lambda 2, lambda 3 are not a normal constants. These are functions on the functions of the context. You see lambda 1, lambda 2, lambda 3, these are functions on the context. This is the context and this is a function. You can make it more complicated and so on and so forth. Okay, so we stop here, okay, and next day we will discuss two advanced smoothing techniques. One is a good Turing method. The second one is Neisser-Ney method, right? And then we'll talk about perplexity, and we'll see how perplexity is linked to entropy, specifically cross entropy. Okay, thank you.